that I want to show you. This is one of my favorite subjects. This explains why my house is such a mess. So you'll see what I mean. I think we talked about these three terms earlier when we talked about the heat transfer, the thermodynamics. And so basically, if you're a picture person, we have the system of interest. And then around the system, we have the surroundings. And then those two together, we have the universe. Okay. And actually, we're going to talk about kind of, and it could be heat, but we're going to talk about work done, from the surroundings onto the system, from the system onto the surroundings, work done, and I can't remember the other thing. But that's kind of what we have going on. So this actually, if you want to put a star on this slide, this is actually the theme of kind of what entropy is all about. Just naturally, and we're going to use the word spontaneous, just naturally, what things like to do is they like to get rid of their energy. Okay? The universe systems tend to want to get rid of their energy. The other thing is they want to get rid of their matter. So it's the dispersion of energy or getting rid of energy, and the dispersion of matter. These are what I say kind of like falling out of bed. If falling out of bed is spontaneous, then these are just kind of like, they just tend to want to do that. Okay? That's the law of the universe. So the word is spontaneous. So if falling out of bed is spontaneous, then it must mean one of these things are true. Falling out of bed must mean that I'm dispersing my energy, or I'm dispersing my matter, or I'm doing both if it's spontaneous. Something that's spontaneous has to be that, or both of those things. If it's spontaneous, if it's just going to happen. Okay. I'm trying to think now. Falling out of bed, I probably am dispersing my energy because I have less potential energy because I'm a lower height. I don't know about dispersing my matter. So trying to kind of talk you through this idea of dispersion of matter, dispersion of energy, and spontaneity. The capital T here means temperature. So this just means that the X is hotter than the Y. That's it. X is hotter than the Y. And they're segregated. Well, if we let them come in contact, and this actually is something we talked about thermodynamics. If we let them come in contact, one of the cool things I think is you can visually picture the X's will have a lot of kinetic energy. I'll kind of show an arrow that shows that they have a lot of kinetic energy. The Y's not so much. Now that would be the kinetic energy of the particles there. So the X's mix it up with the Y. So you can actually see when they're brought in contact, the heat is going to flow from where it's hot to where it's cold. And the way that the heat's going to flow is it's going to be transferred from molecule to molecule. So those hot ones going faster are going to hit the slow ones. The slow ones are going to pick it up a little bit, and then the hot ones are going to lose a little bit. So energy will be conserved. So dispersion of energy. This actually would be a spontaneous thing, right? Might even be dispersion, well, assuming that there's no movement of matter, but dispersion of energy and dispersion of matter is very spontaneous. Similarly, so we're going to kind of try to see where matter is dispersed here. So we have a gas in this chamber, empty over here. Spontaneously, what's going to happen if I open that stopcock? We're going to go over. Spontaneous. It's the dispersion of matter. Okay? So if we kind of look at it back and forth, from the left to the right is spontaneous. But check this out. From the right back to the left is non-spontaneous. And this kind of goes back to my cluttered house. It's natural for matter to become dispersed. It's spontaneous. Okay? In order for matter to go back to where it's supposed to be, okay, it's not spontaneous. So, state functions, when we talked about enthalpies, I think enthalpy comes to mind, and actually, Unit 5, we're going to talk about 3 thermodynamic quantities that are state functions. And to me, a state function, when I talked about it before, I might have mentioned a bank account. So, like you start out with this much money, okay? Let's see how, oops, sorry, I better do this way. You start out with this much money, if this is increasing money. Oh, goodness, increasing money. So you start, okay, and you could win $1 million, okay? And then you could fritter away $1 million plus, okay? And then you could go back to your normal job. As I've just shown you, like this sort of scenario, it's independent of past, so actually there's no change here. No change in money. Delta money, 0. Even though it went all over the place. And that's the same thing with, that's what a state function is. We say it is independent of path, independent of the path taken. It happens. I'm telling you, win the lottery. I'd still do it. What a fun roller coaster. Okay. So entropy, and one of my things is when I learn words, the first letter of the word I can focus on. So one of the things that drives me nuts is enthalpy and entropy. Enthalpy, entropy. Do you see how close they are? They mean different things, but actually they're actually related. But anyway, entropy is by definition a measure of how disordered a system is. How disordered the system is. And to understand how ordered or disordered the system is, we need to look at what's called kind of these levels, these kind of how it's hanging out. Okay. So, if you have something that's kind of complex, and I'm going to try to show you some examples, they're from OpenStack. I'm trying to think of something that's complex. Oh my gosh, on Facebook the other day, I saw it looked like a flower, but it was like a praying mantis. It's a tiny little, it looked like a leaf praying mantis. It was adorable. I mean, how complicated is that organism? Very complicated. So the more complicated something is, you can think of it as actually being more disordered. It's got more possibilities to break. I don't know. Okay? The more complicated something is, the more entropy there is. Okay, so microstates. I'm going to show you kind of some possibilities of, some scenarios. And again, the more complicated it is, the more microstates something can have, okay, then the more entropy we say it has. So this is an OpenStack figure. So the thing here is you can kind of see the red, green, blue, and yellow. So it's like a little game. We have 4 unique dots because of their colors, and we need to go ahead and we've got 2 boxes. And what are our let's play dominoes kind of. What are possibilities to having what are possibilities here? So in this first case, I have all 4 dots in different colors in one box. And I only have 4 dots, so that's it. Second scenario, I'm going to kind of break it up. I'm going to leave 3 dots in the first box, and I'm going to take one of the dots and I'm going to move it over. So the first scenario with all the 4 dots clustered together, low entropy. Low entropy. Higher entropy here. Okay, more microstates. What did I do? Well, I allowed one of the dots of the 4 various colors to move over into the second box. Well, what if we mix it up and we say, all right, I'm ready to go ahead and let 2 dots stay here and let 2 dots of different colors go to the next box. So instead of 1 to 4, now we've got what? 6 different microstates there. 6 different possibilities. It's like a statistic thing, isn't it? Well, I'm migrating from the left box to the right box. Let's go ahead and continue the migration to the right box. And continuing the migration to the right box, I'm going to go ahead and have 3 in my right box and now 1 in my left box. And can you see, to me, B and D look kind of like mirror images? similar chaos, similar entropy. And then the last thing is I have everything migrated to the right box. So I'll put A and E equals low entropy. And I'll put C, I'll put the highest entropy. Highest disorder. And spontaneously, actually, if you give the system, how do I say this? Spontaneity would say, how do I say this? We'll go from ordered to disordered. Another word to say ordered is low entropy to high entropy. So what if I put an arrow underneath that arrow? You know how we have equilibrium arrows? What would that be? It wouldn't be spontaneous, it would be non-spontaneous. Not to say it won't happen, but it won't happen on its own unless, and I hate to throw something else at you, and we'll kind of talk about this as we talk about disorder, unless it is accompanied by dispersion of energy. Which reminds me, here we go. From left to right, spontaneous, I'm going to put dispersion of matter. Does it look like dispersion of matter? When you compare like A and E to C. And then under non-spontaneous, I would say matter coming together. Oops, matter, M-A-T-T-E-R. All right. Cool. Yeah, my house is like C. Sometimes it's like A and E. But so, let's see. This is a heat flow sort of experiment. In this first one, we had 2 units of heat. I was looking at this now. What are you trying to tell me what this says? So in all of these, actually, I have 2 units of heat. In the first case, I'm keeping the 2 units of heat on A and B. Okay. The next possibility, I'm going to disperse the heat. I'm going to keep 1 unit of heat in my A and B, and 1 unit of heat is going to go over to the next box, C and D. But we still have some possibilities here. A and B can have, the unit of heat on the A and the unit of heat on the B, and then, it can be unit of heat on the C and the unit of heat on the D. 4 possibilities. And you know what's coming next. I'm going to go ahead and put, now the heat is going to migrate all the way over to my right box. There again, if it's over in my right box, I can put both units of heat with the C, spread out the heat within my box, or both units of heat with the D. So which one has the most microstates? B. Mm-hmm. So this is the most dispersion of energy. And so this one actually, sometimes in this topic we use the word, we've used favored before, like is it product favored or reactant favored? I'm going to put the word favored up there. So that system is actually favored, or that scenario. Favored over A and C. Dispersion of energy. It's a nice little visual. The greater the disorder in the system, now keep your mind, the system, that's not an accident to use that word. So system is a system. The greater the disorder in the system, okay, the larger its entropy. So disorder, high entropy. Low disorder, or more ordered, right? Less entropy. I love the word chaos. It's chaos, I tell you. Okay, disorder, chaos, randomness. The symbol we use for entropy is the capital S. And units for entropy are going to be units of energy. And we have to say what temperature this entropy is existing at. Units of energy per mole Kelvin or energy per Kelvin. For absolute entropy, I'm not sure. I have to double check what that is. Okay. So do you remember when we talked about enthalpy? Oh my gosh, with an H, right? And it's easier to sink your teeth into the change in enthalpy than the specific enthalpy. It's the same thing with entropy. We oftentimes talk about the change in entropy, what you start out with compared to what you end with. Okay. So things that go into measuring entropy are heat and temperature. And actually heat, how does that go? If your experiments occurring at constant pressure, we said that the change in thermal energy is equal to the change in enthalpy. So anyway, here we go. So your change in entropy, delta S, and by the way, if you dig up that sheet I gave you several weeks ago for Unit 2, you're going to see this on there. This in this purple box will be on the sheet that you have in your test. Change in entropy is equal to Q. Now if you're like, I've seen Q before. Yes, you did. Q is equal to M C sub P delta T. It's one of the things we had in Chem 1. And Q was the change in thermal energy. So change in entropy is equal to the change in thermal energy divided by absolute temperature. All right, cool. Well, some general things about entropy. And this, I like things that make sense, and so I totally buy this one. Can you almost, we've done the whole boxes, solid, liquid, gas, you know, and I think you're going to see maybe a figure, but can you see where if stuff is a solid, it's really ordered? Stuff is a gas, it's not ordered at all. Okay, so the gas has high entropy and the solid has low entropy. And this kind of goes back to my, I think it was like a little praying mantis. It's small, it looked like an bucket. Anyway, so the more complex things are, the higher entropy it has too. Simpler structures have a low entropy. So simple, low entropy. Complex is high entropy. This kind of makes sense too. Let's just say that you have a chunk of solid minding its own business and liquid minding its own business. It's honestly more ordered than when you go ahead and take your solid and dissolve it in your liquid. So it's chaotic then. Okay, so you increase entropy by making a solution. But here's a different one for you. What if you take something that's already chaotic? It's not a solid now. You take those gas particles that are just crazy and you dissolve them in liquid water. Okay? Actually, you're rounding them up, making them more ordered by doing so. So dissolving a gas in a liquid will decrease the entropy as they were by themselves. As the attraction between ions and ionic solids decrease, the entropy increases. So the attraction decreases, so there's less and less of a hold on each other. Okay, so you're on the, think of it as you're on the cusp of being chaotic. Okay, if you've got a strong bond between each other, low entropy. Weak, high entropy. So this is kind of what I showed you before. Lowest entropy for solid, highest entropy for a gas. And you can kind of see these delta S's, change in entropy. So change in entropy increases from left to right, right? And change of entropy decrease, or the change in entropy actually will be a negative number here. So we'll get to this, I don't know if Friday or not, but these delta S's are positive. Remember how we had delta H's that were positive were what? Endothermic. Delta H's that were negative were exothermic. So also down here, these delta S's are negative. Sorry if you can, negative. Can't read, are positive. So this is kind of showing you the change in entropy. We have these abrupt changes in entropy at the transitions. So I think, hopefully this makes sense to you. This is a solid, liquid, gas. We're jacking up the temperature, and of course it's going to melt here, and it's going to evaporate here. So we have a jack up in the increase in entropy as it transitions from a solid to a liquid. We have another abrupt increase in entropy as it goes from a liquid to a gas. And then the other thing is, just when it's staying a solid or staying a liquid or staying a gas, if we jack up the temperature, don't you think it's going to go faster and be a little more chaotic there? So that's kind of why those, you kind of have a gentle slope. Not abrupt. And this is, seems like a Chem 1 thing, but if you were to, at any given time, kind of take a population of particles at two different temperatures and to see how fast they're moving, that's what kinetic energy is. You would see at the cold temperature, which is T1, you kind of have this sort of distribution at the colder temperature. At the warmer temperature, okay, you have actually, fraction-wise, I guess, the fraction of molecules with, it's more spread out. This is not like how much kinetic energy they have. This is the fraction that are at that kinetic energy. This has more kinetic energy at the higher temperature. So if, let's see, this would be, maybe this is maybe 80%. Up here is 100%. Okay, so half of 80, 40%, 20%. So this is saying like 40% at the higher temperatures, for instance, 40% have this higher kinetic energy. Okay, and then here it's saying 80% at the lower temperature have this kinetic energy. So this is a lower Ke, and this is a higher Ke. They look like it's called a bell curve. And so the higher temperatures, not only are they moving faster and more chaotic, but the temperature distribution is more. So the dispersion of energy at the higher temperature. This is the one I told you a minute ago. If you have a blob of solid and you're going to put it in your liquid solvent, okay, and actually it becomes more chaotic over there on the product side. So this says, actually, it looks backwards, but it just says when you dissolve the entropy of the solution, which is over there, is greater than the individual entropies of the solid and liquid. Here's one for you. If you you have to, in order to think through this, you have to picture this vial of water, just clear, vial of water, plain. And then you picture dripping liquid solute in your water solvent. Okay, so food coloring, drop of food coloring. So as it was in the food coloring bottle, it was more organized. Here it's more spread out. So this is a more, that's the dispersion of matter. This is more chaotic than it was before you made it. So here's my vial before, and here's my little dropper, getting ready to drop it in there. That's my food coloring. So this has less entropy. And this has more entropy. Oh, goodness. dispersion of matter. Makes sense. So remember a minute ago, so this semester I'm going to still think about that cute little praying mantis that was about the size of a, I'm going to have to play that for you guys, or put a link on Twitter or something. So that kind of goes along with this. We have these 3 hydrocarbons, increasing complexity, increasing number of carbons. And so you can see the entropy, symbol S, that little superscript, that little, we're going to call this a knot, S knot, K-N-O-T instead of N-O-T. That just means at standard conditions, which will be the same as standard conditions for our enthalpy. Entropy, see what I'm saying? Entropy and enthalpy. So yeah, the entropy for propane with 3 carbons is 270.3 kilojoules per mole per Kelvin versus 186. Here's where I'm gonna kind of diverge a little bit and take you out to